Welcome to this explainer. Okay, I am absolutely thrilled to dive into this with you today. We're unpacking some seriously fascinating engineering that is, quite literally, keeping the lights on around the world. We're talking about the complex, deeply integrated systems that stabilize our modern power grids. I mean, think about it. If you've ever wondered exactly how we take highly unpredictable, intermittent, renewable energy, like when the wind suddenly dies down or the sun ducks behind a cloud, and somehow turn that into a rock-solid, reliable power supply, well, you are in the exact right place. Let's get into it.
On the outside, these things just look like, rows of oversized, plain white shipping containers sitting quietly next to solar panels or wind turbines. But definitely don't let that simple exterior fool you. Inside those unassuming boxes, it's a densely packed marvel of modern electromechanical engineering. And before we zoom all the way into the microscopic digital tech running the show, we really need to grasp the sheer scale of these deployments out in the wild.
So what exactly are we looking at here? Well, BESS stands for Battery Energy Storage System. At its core, it's this massive, utility-scale setup that stores energy when generation is super high but demand is low, and then it discharges that energy right when demand peaks. It's essentially the ultimate shock absorber for the power grid. By storing this energy, BESS solves the fundamental problem of renewables, bridging that huge gap between when power is made and when power is actually needed. And to make this dense engineering super easy to grasp today, we're going to use a sort of anatomical analogy.
So here is our roadmap. Number 1, anatomy of energy storage. Number 2, the brains, BMS explained. Number 3, keeping it cool. Number 4, fire safety and explosion control. And number 5, securing the digital grid. Section 1, anatomy of energy storage, the core components.
Okay, let's dive right into this and start with the macro view. Imagine we're pulling open the doors of that shipping container to look at the physical hardware and the high-level software that makes a BESS tick. I want you to think of these core components as the vital organs of our system. First, you have the batteries themselves. That's the muscle and the actual energy source. Next up is the PCS, or power conversion system. Then we have the EMS, which is the energy management system. Over in thermal management, we've got the HVAC system, acting kind of like the sweat glands. And finally, the absolutely critical BMS, or battery management system. Let's look at how all these organs interact. First up, the PCS, or power conversion system. This essentially acts as the digestive system of the BESS. You see, batteries natively store and supply direct current, or DC voltage. But as we know, our electrical grid runs on alternating current, or AC. So the PCS takes that raw DC power from the batteries and digests or converts it. For example, it might convert it to 690 volts of AC power, which is then fed into a transformer to be massively stepped up, sometimes all the way to 34.5 kilovolts right before it hits the main grid substation. Literally, without the PCS, all that stored battery energy is completely useless to the grid.
Now, sitting right above the PCS is the energy management system, or EMS. Sticking with our biology analogy here, the EMS is the conscious brain of the container. It's the big boss. It provides all the high-level coordination, telling the system exactly when to charge and when to discharge based on what the grid demands. It also handles interoperability, ensuring the power converters, the thermal systems, and the batteries are all talking to each other seamlessly. And crucially, it holds the power for complete system shutdown control if anything goes wrong.
Section 2. The brains. BMS explained. Right beneath the conscious brain of the EMS sits the battery management system. Think of this as the autonomic nervous system of the pack. The BMS is tirelessly working in the background to protect the health of the individual battery cells. Now, what's really interesting about this is how it actually functions. The BMS is constantly monitoring the state of charge, or SOC, as well as the voltage and temperature. If a cell gets a bit too hot or takes in too much current, the protection function immediately kicks in to physically isolate that battery. And perhaps most elegantly, it does this thing called balancing. Because cells naturally degrade at different rates, the BMS actively equalizes the charge across all the cells in a string. This prevents the healthier cells from dangerously overcharging while they wait for the weaker cells to catch up. Pretty smart, right?
And to pull all of this off safely, especially in high-energy utility applications, the BMS has to operate at just staggering speeds. We're talking about critical measurements for voltage and current being sampled at 10 to the power of -3 seconds. That is literal milliseconds. This absolute precision is non-negotiable because modern lithium-ion cells simply do not tolerate overvoltage. By sampling data this incredibly fast, the BMS can instantly trigger physical contactors to isolate the battery pack before a tiny electrical anomaly cascades into a full-blown catastrophic failure.
Section 3.
Keeping it cool. Thermal management.
As you can imagine, charging and discharging these massive amounts of energy generates some serious heat. It's the battery equivalent of a really heavy workout. So to manage this and keep this system from overheating, engineers use a few different methods. Air cooling is the simplest, and it uses the least energy, but honestly, its efficiency is pretty low. So for large-scale grids, we step up to liquid cooling. This forces coolant through plates right near the cells for much higher efficiency. But the true cutting edge, that's moving toward phase-change materials and immersion dielectric fluids. In these immersion systems, specialized electrically insulating fluids physically surround and directly touch the battery cells. It immediately absorbs the heat the actual second a thermal event begins. It's a real game changer.
Section 4. Fire safety and explosion control. Okay, so what actually happens if the thermal management completely fails and a cell goes into thermal runaway? Because the deployment of BESS technology has grown so incredibly fast, safety standards have had to evolve aggressively to keep up. Enter NFPA 855. This is the rigorous industry standard that governs the installation, the fire codes, and hazardous mitigation for stationary energy storage systems. And the task forces behind the standard, well, they've recently instituted a massive paradigm shift in exactly how we handle battery fires. For decades, the gold standard for fire safety dictated that you immediately suppress a fire to put it out. Simple enough, right? But lithium-ion battery fires are completely different. They actually generate their own oxygen as they burn. So the totally counterintuitive paradigm shift in these new NFPA 855 standards moves completely away from traditional fire suppression and instead heavily prioritizes explosion prevention. Why? Well, if you suppress a battery fire without fully cooling the core, the batteries just continue to off-gas highly flammable vapors. If those trapped gases fill the enclosure and suddenly mix with oxygen, say when a first responder opens a door, it triggers a massive explosion. Tragically, this exact scenario happened at a facility in Surprise, Arizona back in 2019. So, the crucial point here is that this shifts the entire engineering philosophy. Today, the current industry best practice combines explosion prevention with fire containment. The idea here is that fires are allowed to burn out in a controlled fashion while protecting nearby equipment. In many scenarios, if a fire starts inside an enclosure, it is intentionally allowed to burn out completely safely. By letting those flammable gases combust as they're generated, we totally avoid the risk of a sudden, catastrophic explosion. Plus, it eliminates the major risks of stranded electrical energy and contaminated water runoff from firehouses. Now, to ensure this controlled burn strategy actually works out in the real world, operators rely on large-scale fire testing, specifically known as UL 9540A. I mean, before a BESS site is even built, these systems are literally set on fire in specialized labs. They do this to absolutely verify that the complete combustion of one single enclosure won't cause a thermal runaway event in the unit sitting right next to it. It is all about precise spacing, proven through extreme physical testing. Section 5. Securing the digital grid. Okay, now that we've explored the physical anatomy, we really have to look at the invisible digital landscape. Because BESS relies so heavily on rapid digital communication, like that EMS and BMS software we talked about, it operates within a digital environment where cyber threats are increasing in frequency every single day. But unlike legacy power plants that often run on outdated, unpatched software, modern energy storage systems are built with cybersecurity integrated from day one. The true challenge isn't just protecting the on-site hardware, it's actually securing upstream vulnerabilities in the supply chain to block sophisticated attackers before the equipment is even assembled. Ultimately, when securely designed, fully integrated, and properly maintained, a battery energy storage system doesn't just store power. It actively enhances the resilience of the entire grid. It acts as both a physical shock absorber for electricity and a hardened digital fortress against operational disruptions. Which leaves us with a pretty crucial question. As these massive BESS networks continue to scale across our landscapes, how will the invisible digital armor we write today evolve to protect the physical grid of tomorrow? It's a brilliant intersection of heavy physical engineering and cutting-edge software. Thank you so much for joining me on this explainer. I really hope you walk away with a much deeper appreciation for the complex anatomy stabilizing our grid. Keep learning, and I'll catch you